Hi everyone, welcome to day 2 of trigonometric functions. We're going to keep working on what we know about sine and cosine and tangent and secant and cosecant and cotangent today. We're going to explore other problems that we can solve using these ratios. So let's start day 2. So after our warm-up, okay, for the left triangle, find the ratio for the tangent of b, or tangent of beta. And then for the right triangle, I want you to solve for side length x. And when you're ready, unpause the video, we'll take a look at some answers. Okay, so to see these problems in action, okay, I start from beta, I label the opposite, the adjacent, and the hypotenuse. So the tangent is the opposite divided by the adjacent, or 15/9. And now to solve for the sides, once again, label my picture, have it nice and drawn out. Opposite and hypotenuse, I'm going to use sine here, and I'm going to solve for x. Since x is in the denominator, we'll multiply both sides before it, and then isolate the variable. We can do that. Set up the equations, pick the correct ratio. Now today we're going to learn about some special types of triangles. So we could be given this, and in this problem you actually are given enough information even though the picture does not look like it. So this is a 45, 45, 90 triangle where side length OM is 2. I want you to tell me all 6 ratios, the sine, the cosine, the tangent, the secant, the cosecant, and the cotangent. So step 1, always draw the picture and think about what information we're given. Okay, it tells us the 45, 45, 90 triangle, which is going to be very, very helpful. So, since it's an isosceles right triangle, okay, if these two angles are 45 degrees, which I'll label in here, 45 and 45, then the opposite sides of the two legs have to be congruent. And then we could use Pythagorean theorem to find the hypotenuse, okay, which is square root of 8 or 2 square root of 2. Now, I'm going to write 2 square root of 2. Okay, I'm going to show you a pattern. Okay, in a 45, 45, 90 triangle, if the side length is x, okay, then the two legs are x, and the hypotenuse is x times the square root of 2. Works for every 45, 45, 90 triangle. You don't have to use Pythagorean theorem every time, but you're welcome to. Now I have a fully labeled triangle. Now I can use my 6 trigonometric ratios. So this diagram, okay, the sine is opposite over hypotenuse, 2 divided by 2 square root of 2, and I simplify that. Okay, and the way I do that is the 2's are going to cancel out, and I'm left with 1 over the square root of 2, and I multiply that. We learn to rationalize the denominator by multiplying by the square root of 2 in the numerator and the denominator, and that's how I rewrite 2 divided by 2 square root of 2. Cosine is the same thing. We're going to learn that sine of 45 and cosine of 45 are the same. And that tangent here is opposite over adjacent, so tangent is 2 divided by 2, which is 1. Now, to find the other ratios, we take the reciprocals. So if you take the reciprocal of sine, you get cosecant, and the 2's cancel out. Same thing with cosine and secant. And cotangent, the reciprocal of 1 is 1. So we're going to use a lot of Pythagorean theorem, labeling sides, so we can find the trigonometric ratios. We found all 6 of them. Now we saw that in a 45, 45, 90 triangle, the two legs are the same length. Therefore, the sine of the angle and the cosine of the angle are the same. Since the sine and the cosine are the same, the cosecant and the secant are the same. And since the tangent is 1, the cotangent is the reciprocal, which is 1. Okay, and if you put sine of 45 in your calculator, you're going to get square root of 2 over 2. Yeah, but your calculator is not going to give you that. Your calculator is going to give you the decimal approximation, which is 0.7071. Now, this triangle is not a 45, 45, 90 triangle. They're telling us it's a 30, 60, 90 triangle. And it's telling us the measure of angle J is 30 degrees. So this right here is actually half of an equilateral triangle. If I drew another triangle below this, you'd see an equilateral triangle. Okay, so we got to find the 6 trigonometric ratios, and we're going to do that, okay, by using Pythagorean theorem. Okay, and this simplifies to 4 square root of 3. So in a 30, 60, 90 triangle, we're going to see this ratio that if this, we can find the smallest side length, which is opposite 30 degrees. So in this case, KL is my smallest length. Then the medium length is x times the square root of 3. And my hypotenuse is going to be double my small leg. And that's always going to work. So in this case, my small leg is 4. My medium leg is 4 square root of 3. And my hypotenuse is 2 times 4, which is 8. Now, once again, I have my diagram fully labeled, so I can find the ratios. Okay, and in the secant, in the case of secant, in the case of tangent here, I need to remember, simplify and rationalize the denominator. Write down the ratio, rationalize the denominator. We can do that. So now it's your turn. Okay, the hypotenuse is 5 square root of 2. I want to know the sine and the secant. Pause the video, draw the picture, do all the steps you think, and then we'll come together in a moment and see if that you got the right answer. Okay, so here we go. We'll take a look at it. Okay, I told you the hypotenuse is 5 square root of 2, which means that both legs have to be 5. Okay, that means the sine is 5 over 5 root 2. Okay, so if I do the sine, it's opposite. So sine 45 equals opposite over hypotenuse. And those cancel out, and I multiply by root 2. So this should say root 2 over 2. Yeah, that's a Mr. Minowitz mistake. And then the secant should be the reciprocal, which is just root 2. Okay, and once going to show the sign, I multiply the denominator by square root of 2, the numerator by square root of 2, and then I have square root of 2 over 2. That's how I got my sign. Okay, and secant is 1 over cosine, and cosine and sine are the same in a 45 degree or 45, 45, 90 triangle. If you can draw it, you can, and remember the ratios, you can do these problems. Now let's explore some identities. So ones that are reciprocal of each other, we already talked about those. Sine and cosecant are reciprocals of each other. Cosine and secant, tangent and cotangent. So if you know one ratio, you know another ratio. You really know 2 at a time. So sine, we could take and flip the fraction and we get cosecant. Now, the next question is, we got to think about how are the sine and the cosine and the tangent related to each other? Now, this is a really cool theorem that we're going to see, and it always works. So really, you know a whole lot of information when you're just given one angle. So let's take these two angles, alpha and beta. Now alpha and beta have to add up to 90 degrees because the three angles have to add up to 180. So if I know beta, I know alpha, and if I know alpha, and I know beta. And what's really awesome is that the sine of one is the same as the cosine of another. The sine of, okay, if I'll call these sides A, B, and C. The sine of alpha is A over C. The cosine of beta is A over C. So the sine of one equals the cosine of another. The cosine of one equals the sine of the other. Notice here that the cosine of alpha is equal to the sine of the beta. These are called cofunctions. So if I said the sine of 30 equals something, and the sine of what 30 we're going to learn equals 1.5, we also know that that's equal to the cosine of 60. Because the two angles are complementary. So two complementary angles, two angles that add up to 90 degrees, one sine is the other cosine. So let's look at this problem. Okay, right angle, I have alpha and beta. I know that the sine of alpha is 8 over 17, and the cosine of alpha is 15 over 17. And I want to find the sine of beta and the cosine of beta. And there's multiple ways I can do this. Okay, I probably would label the triangle from alpha and then just look at beta and find the ratios. But sine of alpha equals cosine of beta. So if we know sine of alpha, we know cosine of beta. Okay, so if sine of alpha is 8 over 17, then the cosine of beta is 8 over 17. Cosine of beta equals 8 over 17. And we can show this on the triangle because the sine is the opposite over the hypotenuse. And it also says the cosine of alpha is 15 over 17. And then the cosine of beta, if we're looking for at beta, then we have the opposite, the adjacent, and the hypotenuse. So we can see that the cosine of beta is 8 over 17. There's a lot of different ways we can do it. I always like drawing the picture, but I also like to know that the sine of alpha equals the cosine of beta, and the cosine of alpha equals the sine of beta. So now you try, think about these triangles. Okay, what would you know about the tangent and the cotangent of different angles? So in this case, the tangent of alpha equals the cotangent of beta. And let's see why. If I'm looking at alpha, we'll start with alpha and we'll put alpha in the blue pen. Oh, that's not blue, that's shiny like that. Opposite, adjacent, hypotenuse. So the tangent of alpha equals opposite over the adjacent. Or use O and A. Now if we're looking at beta, the tangent is A over O. So the tangent of beta equals A over O. Now we see the cotangent of beta is the reciprocal. So the cotangent of beta equals the tangent of alpha. So if I know the tangent of an angle, I know the cotangent of another angle. If I know the sine of an angle, I know the cosine of its complement. Okay, so the tangent of alpha equals the cotangent of beta. And same thing, sine of alpha equals cosine of beta, and cosine of alpha equals sine of beta. All these theorems you'll start to see as we look at more side lengths and ratios on the triangles. So what we see here in this lesson, label the triangle, draw the picture. We know how to solve after we set up the ratio, the sine, the cosine, the tangent, the cosecant, the secant, or the cotangent. Okay, we learned that if that's theta and this is beta, we learned the sine of theta equals the cosine of beta. We also learned that the tangent of theta equals the cotangent of beta. And we learned that they're reciprocal ratios. Now these are the basics, and next time we're going to learn about something called the unit circle and how to find the sines and cosines and tangents of a whole lot of special angles that we deal with in triangles.